Year 1790, St. Petersburg. The Alexander column, weighing approximately 600 tons, was erected without bolts. No one has explained the method of transport, erecting it upright. The Alexander column stands at the center of St. Petersburg with a kind of composure that feels deliberate, almost restrained. It does not lean. It does not announce itself with ornament or structural flourish, and it does not rely on visible reinforcements to justify its presence. It is simply there, rising from the open space of the square, a single shaft of granite set upright against the sky. People pass around it every day, some glancing up briefly, others not at all, because the column has long since blended into the visual grammar of the city. It belongs, and because it belongs, it rarely invites sustained attention. Yet the longer one looks, the harder it becomes to reduce the column to a symbol or a background feature. It is not assembled from sections. It is not framed by metal braces or anchored by exposed fastenings. It is a single piece of stone, quarried as a whole, shaped as a whole, and raised as a whole. Its mass approaches 600 tons. Its height and proportions are such that the eye instinctively searches for evidence of restraint, for some visible system holding it in place. None appears. The column stands upright by virtue of its own weight, balanced on its base, relying on gravity rather than attachment. This fact is not hidden or disputed. It is stated plainly in historical descriptions. No bolts were driven through its body, no internal metal spine runs through its core, no external framework locks it into position. The column is not clamped or pinned. It rests, precisely aligned, its center of mass calculated well enough that it has remained stable through centuries of wind, frost, vibration, and seasonal change. The stone presses downward, and that downward force is sufficient. The effect is subtle but unsettling. Modern intuition associates stability at scale with redundancy. Large objects are expected to be secured, backed up, reinforced. When something heavy stands freely, unsupported in appearance, the mind instinctively questions the margins of safety involved. With the Alexander column, that question never fully resolves itself. The stone is too large to ignore, yet too calm to provoke alarm. It does not look precarious. It looks complete. To stand near its base is to feel the imbalance between what is seen and what is understood. The granite surface is smooth, its curvature consistent, its vertical line uninterrupted from base to capital. There is no visible sign of strain, no cracking, no distortion. The column does not communicate effort. It communicates finality, as if the most difficult part of its existence occurred elsewhere, long before it reached this position. That elsewhere matters. Before the column could stand here, it had to be extracted from the earth as a single mass. Before it could be raised, it had to be transported across distance. Before it could be balanced upright, forces had to be applied gradually and precisely enough to avoid fracture or loss of control. Each of these stages carries risk. Each demands coordination, and yet, when the finished column is encountered, those risks are no longer visible. They have been absorbed into the result. What remains is a form that asks a quiet question without insisting on an answer. How does a 600-ton stone come to stand like this, unsupported in appearance, without leaving behind a clear explanation of the methods that brought it here? The question does not accuse. It does not demand revision. It simply arises from the physical reality of the object itself. The column stands. The stone holds. And in the space between observation and explanation, something feels incomplete, not because the structure is unstable, but because our understanding of how it came to be feels lighter than the weight it continues to carry. In the standard historical account, the Alexander column belongs firmly within the political and cultural logic of Imperial Russia at the turn of the 19th century. St. Petersburg had already been established as the capital, a city intended not merely to function as an administrative center, but to communicate authority, continuity, and alignment with European power. Monumental architecture served this purpose. Columns, arches, and expansive squares were visual statements, designed to translate abstract ideas of rule and victory into physical form. Within this context, the decision to erect a monumental column was neither unusual nor extravagant by the standards of the age. The late 18th century was a period in which imperial symbolism mattered deeply. Russia's ruling elite sought to anchor legitimacy in stone, bronze, and ceremony. Monuments were commissioned to commemorate military triumphs, dynastic stability, and the endurance of the state itself. The Alexander Column emerged from this tradition. It was conceived as a commemorative structure, a vertical marker in the urban fabric that would embody permanence and strength. Its placement within a central square was deliberate, aligning it with surrounding institutions of power and public life. Historical sources attribute the realization of the column to recognized figures within the architectural and engineering establishment of the time. Architects provided the aesthetic vision, ensuring the monument conformed to classical proportions and visual harmony. Engineers were responsible for translating that vision into a stable structure, applying known principles of statics and material behavior. The project was planned, approved, and executed under imperial authority, with access to resources, labor, and expertise that were unavailable to most builders of the period. Accounts of the construction process, as preserved in official histories, describe a sequence of stages that appear orderly and controlled. The stone was quarried from a suitable source, selected for its quality and integrity. It was shaped according to design specifications, transported to the city, and prepared for erection. The final raising of the column is presented as a feat of organization and skill, carried out successfully through careful planning and disciplined execution. The narrative emphasizes competence rather than risk, framing the operation as demanding but achievable within the technical framework of the era. Within this version of events, there is no anomaly. Large monuments existed elsewhere in Europe. Skilled craftsmen had long worked stone. Engineers understood leverage, balance, and load. The column's existence is treated as confirmation of these capabilities rather than as a challenge to them. The focus remains on intent, symbolism, and outcome. The monument stands because the state ordered it, the professionals designed it, and the labor force carried out the work. The story proceeds cleanly from conception to completion. When attention shifts from narrative to measurement, however, the material characteristics of the column introduce a different dimension to the discussion. The Alexander Column is not merely tall, it is massive. Its weight approaches 600 tons, concentrated into a single, uninterrupted shaft of granite. Its height and diameter follow classical ratios, producing a slenderness that accentuates its vertical presence. The stone's geometry is precise. The axis is straight. Deviations from vertical alignment are minimal, remaining within narrow tolerances over the full height of the structure. Balance is central to its stability. Because the column is not mechanically fastened to its base, its center of mass must align closely with its support. Even small miscalculations in geometry or placement could introduce uneven stress, increasing the risk of tilt or fracture. The margins involved are not arbitrary. Granite resists compression well but responds poorly to uneven tensile forces. Maintaining equilibrium in a structure of this scale requires careful control over shape, surface contact, and alignment. Comparisons with other stone columns of the period help to situate the Alexander Column within a broader architectural landscape. Europe possessed ancient examples of monolithic columns, many of them inherited from earlier civilizations. More recent monuments often relied on segmented construction, stacking multiple drums rather than lifting a single piece. This approach reduced risk and simplified handling. Where monoliths were used, their dimensions typically reflected compromises between ambition and practicality. Against this background, the Alexander Column occupies an upper range of scale. Its weight exceeds that of most contemporary monolithic columns. Its proportions are ambitious without appearing heavy. The fact that it was erected in a city built on challenging ground conditions further distinguishes it from monuments placed on more stable terrain. These comparisons do not render the column unique in principle, but they do highlight the level of control required to achieve such an outcome. At this point, the narrative does not break, but it begins to stretch. The historical account affirms that the column was raised successfully. The physical evidence confirms that it remains stable. Between those two facts lies a space defined by physics rather than symbolism. How was the weight managed during lifting? How closely were tolerances monitored during alignment? What degree of error could be absorbed before the operation became unsafe? These questions arise naturally from the object itself. They do not negate the official story, but they introduce a layer of physical reality that the standard narrative does not dwell on, leaving certain aspects of weight and geometry present, measurable, and quietly unresolved. Granite is a material that does not negotiate. It responds predictably to forces, but without generosity. Under compression, it performs well, carrying immense weight without complaint. Yet under uneven stress, it becomes vulnerable. prone to sudden fracture rather than gradual deformation. Unlike metals, it offers no warning through bending or stretching. When granite fails, it does so abruptly. This property makes it desirable for monuments intended to endure, and at the same time unforgiving during every stage of handling before completion. A monolithic column concentrates these properties into a single object. Its mass is continuous, its internal structure fixed from the moment it is separated from the bedrock. Any flaw introduced during extraction remains embedded for the life of the stone. Any stress imposed unevenly during shaping, transport, or erection accumulates invisibly, stored within the material until it either dissipates safely or expresses itself through cracking. For a column approaching 600 tons, the margins involved are narrow. The stone must be worked with uniform pressure, lifted with distributed force, and supported in ways that prevent localized loading. During cutting and shaping, granite demands consistency. Removing material from one side faster than another introduces imbalance. Uneven vibration can propagate microfractures. Tool paths must be controlled to maintain symmetry, particularly in a cylindrical form where deviations compound along the length. The finished surface of the Alexander column suggests that such control was maintained throughout the process. The curvature is even, the axis remains true. The mass is balanced around a central line that would later define stability when the column stood upright. Transport introduces a different set of demands. Granite tolerates compression but reacts poorly to torsion and bending. When a long, heavy stone is moved horizontally, its own weight creates internal stress along the length. Supports must be placed at calculated intervals to distribute load evenly. Sudden changes in direction, uneven ground, or asymmetric lifting increase the risk of damage. Modern standards for transporting such a mass rely on reinforced cradles, vibration damping, and constant monitoring. In the 18th century, such systems did not exist in recognizable form, yet the stone arrived intact. The most demanding phase comes during erection. Raising a monolithic column from horizontal to vertical subjects it to continuously shifting stress vectors. At intermediate angles, neither compression nor tension dominates fully. Portions of the stone experience bending forces that granite is least equipped to handle. Control over speed, alignment, and support must be precise. Any abrupt movement can introduce stress beyond tolerance. In contemporary engineering practice, such an operation would be accompanied by extensive modeling, redundancy in lifting systems, and contingency planning. The absence of visible reinforcement in the finished column means that all such control had to occur externally and temporarily, leaving no permanent trace. None of this implies that the task was beyond the reach of historical builders. It does, however, clarify the level of technical discipline required. The stone itself sets the terms. Granite does not adapt to methods. Methods must adapt to granite. The Alexander column stands today because, at every stage of its creation, forces were managed within strict limits. The material allowed no shortcuts. From the quarry to the square, the column moved through space before it ever moved through air. The source of its granite lay far from the city, in regions chosen for the quality and size of available stone rather than convenience. Once detached from its original setting, the column became a problem of logistics as much as craftsmanship. Its weight excluded ordinary transport. Its dimensions limited maneuverability. Every kilometer traveled multiplied risk. Historical accounts mention routes and means in broad terms. Rivers and canals formed the backbone of heavy transport. Barges could carry loads that roads could not, provided water levels were sufficient and currents manageable. Overland movement relied on sledges and wheeled platforms, drawn by animals or human labor. Winter offered advantages, transforming soft ground into hardened pathways and allowing heavy loads to slide over ice with reduced friction. These methods were known and used elsewhere, and they form the accepted framework for explaining the column's journey. What remains less clearly described is the integration of these methods into a continuous system capable of handling a single object of such mass. A barge carrying hundreds of tons requires careful balancing to avoid capsizing. Transferring the load from water to land introduces another critical moment, one that demands precise coordination. Overland hauling must account for gradients, turns, and structural limits of bridges or temporary supports. Each transition between modes increases complexity. The sources confirm that transport occurred. They acknowledge winter roads, water routes, and the use of existing infrastructure. They do not, however, provide detailed accounts of how stress was managed at each stage, how supports were positioned along the length of the stone, or how contingencies were addressed if conditions shifted. Breakage, if it occurred, is not prominently recorded. Delays, rerouting, or modifications to equipment receive limited attention. When considered as a system rather than a sequence of anecdotes, the transport of the Alexander Column represents a sustained logistical operation. The stone had to move predictably, steadily, and safely over long distances. It could not be replaced easily if damaged. The margin for error was small. That it arrived ready for erection suggests that the system worked as intended. The absence of detailed description does not undermine that conclusion. It simply leaves the mechanics of success largely unarticulated. The column reached St. Petersburg. It was positioned. It was raised. These outcomes are not in doubt. What remains thinly described is the pathway between origin and destination, a pathway shaped by material constraints, seasonal windows, and coordinated effort. The granite passed through space under conditions that demanded precision, and the stone itself offers the only enduring evidence that those demands were met. The moment when the Alexander Column moved from horizontal to vertical marked the point at which all previous effort converged into a single, irreversible sequence. Until then, the stone could still be supported along its length, its weight distributed across multiple points, its stresses managed through careful placement. Once the lifting began, those conditions changed continuously. As the column rose, gravity redefined how forces traveled through the granite. Compression shifted, tension emerged, and bending moments appeared where none had existed before. This was the phase in which granite is least forgiving. Raising a mass of this scale demands not only strength but control. The force required is not applied all at once, but gradually, balanced against resistance, friction, and the stone's own inertia. At intermediate angles, the column experiences uneven stress, with portions of its length carrying disproportionate loads. A misalignment of even a small degree can introduce torsion. A pause at the wrong moment can concentrate force where the material is weakest. Granite does not accommodate these errors. It neither flexes nor absorbs shock. It holds until it fails. Historical descriptions acknowledge that the column was raised successfully, and some accounts reference the use of ropes, pulleys, and coordinated labor. These references establish that a lifting operation took place, but they remain general. They do not specify the configuration of the lifting system, the distribution of force along the column, or the sequence by which tension was transferred from horizontal supports to vertical balance. They do not describe how the rate of ascent was controlled or how alignment was monitored as the stone approached its final position. From a physical standpoint, the critical risk during erection lies in transition. When the column is nearly upright, its center of mass passes through a narrow range where stability is not yet assured, but failure would be catastrophic. At this stage, lateral forces must be minimized. The base must be prepared to receive the load evenly. Any irregularity in the contact surface can produce uneven compression, increasing the risk of tilt or cracking. The fact that the column ultimately stands without mechanical fastening means that the final placement had to be exact. There was no margin for adjustment after the load settled. Modern engineering practice treats such operations with caution. Detailed calculations precede any lift. Redundant systems are installed to prevent uncontrolled movement. Continuous measurements track alignment and stress. None of this language appears prominently in the surviving documentation of the Alexander Column's erection. The accounts confirm success, but offer little insight into the mechanics that made it possible. This absence does not imply improvisation. On the contrary, the outcome suggests planning of a high order. The column did not fracture during lifting. It did not tilt beyond recovery. It did not require correction after placement. These facts indicate that forces were anticipated and managed within acceptable limits. What remains unspoken is how those limits were defined and enforced in practice. Once upright, the column entered a different state entirely. Gravity, which had posed the greatest threat during erection, became the source of stability. The stone settled onto its base, its weight pressing evenly downward. The risks associated with movement ceased. The most dangerous phase was over, and with it passed the need for any temporary systems that may have been used to control the lift. Whatever structures, frames, or arrangements existed during that moment left no permanent trace. The column stands alone, bearing no visible memory of the forces that once acted upon it. When attention turns to documentation, a familiar pattern emerges. The historical record preserves the result with clarity. The column was raised. It stands. It has stood for generations. What it does not preserve in comparable detail are the internal mechanics of the operation. There are no surviving detailed drawings of the lifting apparatus that can be reliably associated with this specific project. No scaled models are described, no reports outlining calculated risks or contingency plans are readily available. The process is acknowledged, but its internal structure is not recorded in a way that allows reconstruction. This gap becomes more apparent when contrasted with what does exist. The finished monument remains intact. Its geometry has not shifted. Its vertical alignment remains true. It has endured seasonal expansion and contraction, ground movement, and the vibrations of an evolving city. Through wars, weather, and time, it has remained stable. These outcomes speak to the adequacy of the original execution. What is missing, then, is not evidence of success, but evidence of method. The absence is one of description rather than substance. The archives confirm that the column was erected, but they do not dwell on how risk was evaluated, how force was applied, or how error was mitigated. They do not present a narrative of trial and adjustment. They move directly from intention to completion. In this sense, the Alexander column embodies a characteristic tension of large historical works. The material object survives with precision, while the procedural knowledge that produced it fades into generality. The column stands as proof that the operation was carried out within strict physical limits. At the same time, the lack of detailed technical documentation leaves those limits undefined in the historical imagination. The stone does not reveal its story easily. It offers stability without explanation. It demonstrates control without preserving a manual. The moment of greatest danger passed without leaving a detailed record of how it was managed. What remains is a structure that confirms capability through its existence and a silence around the exact means by which that capability was exercised. Several scholarly interpretations have been offered to account for how the Alexander column was raised, each grounded in practices known to have existed at the time, and each constrained by the same gap between description and execution. None of these interpretations is implausible, and none resolves the matter fully. Together, they form a field of explanation that remains open rather than closed, defined more by balance than by certainty. One widely cited explanation relies on traditional pulley systems and mechanical advantage. Ropes, capstans, and compound pulley arrangements were well understood by the late 18th and early 19th centuries. These systems allowed relatively small forces to be multiplied through careful arrangement, enabling large loads to be moved gradually and under control. Historical accounts of shipbuilding, dockyard work, and construction projects demonstrate that coordinated teams could apply force evenly over time. In this view, the raising of the column becomes an extreme but logical extension of existing methods. Its strength lies in continuity. It requires no unknown technology, only disciplined application of known principles. Its limitation, however, lies in scale. The number of pulleys, anchor points, and synchronized operations required to manage a 600-ton monolith during rotation and lift would have been considerable. While not impossible, such a system would have been complex, temporary, and vulnerable to small errors, and yet it left no detailed technical record that has survived. A second explanation emphasizes collective labor. Large numbers of workers acting in coordination can generate significant force, particularly when guided by structured command. This model aligns with the broader context of imperial construction, where manpower was abundant and centrally directed. In this framework, the column was raised through sheer organizational capacity. Human effort replaced mechanical sophistication. The advantage of this explanation is its consistency with documented labor practices of the era. The weakness lies in control rather than strength. Human-powered systems are effective at applying force, but less precise in regulating it. Granite, as a material, demands not only power but smoothness and predictability. Managing uneven stress during the critical stages of erection through human force alone would have required extraordinary coordination, and the historical record offers little insight into how such coordination was maintained at the necessary level of precision. A third interpretation suggests that specialized lifting techniques once existed but were not preserved in detail. Knowledge of construction methods can be highly situational, transmitted through apprenticeship rather than formal documentation. When economic or political conditions change, such knowledge can disappear without leaving clear traces. In this view, the Alexander column represents the application of a refined technique that was later abandoned or rendered obsolete. This hypothesis accounts for the apparent gap between outcome and explanation. It allows for a level of technical competence that exceeds what is commonly described without invoking anachronism. Its limitation is evidentiary. Lost techniques usually leave indirect marks, such as similar applications elsewhere, transitional forms, or references in technical literature. In the case of the column, such corroborating material remains limited. Each of these hypotheses addresses part of the problem while leaving other aspects unresolved. Traditional pulleys explain force multiplication but strain under the demands of precision. Collective labor explains power but struggles with control. Lost techniques explain coherence but lack supporting documentation. None can be dismissed outright, and none can be accepted as complete. The column itself does not privilege one explanation over another. It stands as a finished result, indifferent to the categories imposed after the fact. The absence of a definitive answer does not undermine historical understanding. It reflects the nature of inquiry at the intersection of narrative history and material analysis. Some questions persist not because they are forbidden, but because they sit outside the usual priorities of historical storytelling. This leads to a broader consideration of why such questions are rarely foregrounded. Historical narratives tend to organize the past around rulers, events, and symbols. The Alexander column fits comfortably within this structure as a monument to power and commemoration. Its meaning is derived from whom it honors and what it represents, not from the mechanics of its assembly. Within this framework, technical processes are assumed to be subordinate details, resolved implicitly by the existence of the finished object. Engineering questions operate differently. They ask how forces were managed, how tolerances were maintained, and how failure was avoided. These questions complicate narrative flow. They slow the story and introduce uncertainty where clarity is preferred. As a result, they are often condensed or omitted in favor of broader themes. The raising of the column becomes a moment of triumph rather than a sequence of calculated risks. There is also a disciplinary divide at work. Historians are trained to interpret texts, contexts, and intentions. Engineers are trained to analyze systems, constraints, and performance. When monuments are examined primarily through written sources, the physical object becomes illustrative rather than interrogative. Its success is taken as proof that the methods must have existed, and inquiry moves on. Over time, repetition reinforces this pattern. The story is told, retold, and simplified. What began as an implicit assumption hardens into an accepted explanation. The column stands, therefore it was built competently. The details of that competence are no longer considered essential to the narrative. Yet the stone itself does not participate in this simplification. It retains its mass, its balance, and its demands. It continues to embody a technical achievement, whether or not that achievement is described in detail. The question of how remains present, not as a challenge to historical legitimacy, but as an invitation to look beyond symbols and consider process. In this sense, the relative silence around the mechanics of the Alexander column is not an anomaly, but a reflection of how history is commonly framed. Narratives favor meaning over method. Symbols eclipse systems. The column becomes an emblem rather than a case study. And so the question recedes, not because it has been answered, but because it has been placed outside the usual scope of attention, waiting for moments when curiosity extends beyond what is commemorated to how it was made. The Alexander column still stands in the same place it has occupied for generations, unchanged in posture and indifferent to interpretation. It rises from its base without visible restraint, without bolts, without a frame to explain how its balance is maintained. Gravity presses it downward, and that downward force is enough. The stone has endured wind, frost, seasonal expansion, ground movement, and the accumulated vibrations of a living city. Time has tested it repeatedly, and each time the column has answered with stillness. There is something instructive in that persistence. The monument does not attempt to justify itself. It offers no diagram, no inscription describing its method of assembly, no indication of the temporary systems that must have existed during its creation. Whatever ropes, scaffolds, or lifting frames once surrounded it have long since disappeared, leaving no physical trace. The column remains alone, complete in itself. its stability neither explained nor compromised by the absence of visible support. In this way, the Alexander column resists being reduced to a single meaning. It can be read as a symbol of imperial authority, as an aesthetic statement shaped by classical ideals, or as a testament to organizational power. All of these interpretations coexist without difficulty. None of them, however, fully accounts for the physical reality of the stone itself. The column does not merely represent endurance, it performs it continuously under conditions that would expose weakness if weakness were present. What is striking is not that the column stands, but that it stands so quietly. There is no sense of strain in its form, its vertical line remains true. Its mass appears settled, as if the moment of greatest risk passed long ago and left no visible mark behind. The most demanding phase of its existence, the transition from horizontal stone to vertical monument, is now entirely absent from view. Only the outcome remains. This absence shapes how the monument is understood. Without a detailed account of how it was raised, attention shifts naturally toward what it represents, rather than how it functions. The narrative becomes symbolic rather than technical. The stone is admired, photographed, and passed by, while the process that placed it there fades into abstraction. The success of the operation is acknowledged, but the mechanics of that success are rarely revisited. Yet the column itself does not encourage forgetting. Its material properties continue to assert themselves. Its weight is unchanged. Its balance remains exact. The conditions that once made its erection risky still define its relationship to the ground and to gravity. Each winter, each thaw, each subtle shift in the city beneath it renews the original test, and each time the stone holds. There is no need to draw a conclusion from this endurance. The historical narrative remains intact. The monument was planned, executed, and completed within its time. The absence of detailed technical records does not invalidate that account. It simply leaves certain aspects of the achievement less articulated than others. What remains is a question that does not demand resolution. How much do we truly understand about the ways people in the past solved problems that now appear exceptional when viewed through modern expectations? The Alexander column does not insist on an answer. It stands as evidence that solutions existed, even if their full descriptions did not survive. The stone remains upright, balanced by its own weight, carrying forward a quiet reminder that the past often leaves us results without manuals, achievements without explanations, and structures that continue to function long after the methods that created them have slipped beyond clear memory.